Okay, let's see quantum linear regression. All of us are aware about linear regression, something like AW is equal to B format. Of course, there can be the intercept as well. Suppose if I have a linear system of equations, AW is equal to B. If I have to solve it, then the best way to solve it is, of course, there are different ways. One way to find omega or W is this one. Okay. Of course, I find the inverse of A and multiply it to B. That's one version. Gaussian elimination is there. Also, orthogonal transformations where I'll find the eigenvalues lambda. Once I know the eigenvalue for A, I interpret the eigenvalue for A inverse and hence get it would be lambda inverse. Hence, I will do the spectral decomposition and proceed further. Okay, for finding out the W. Okay, yeah, let's see first what exactly is quantum linear regression, then get back to the things related to classical. Okay, now in quantum linear regression is similar to my linear regression. What's the difference? Let me talk about. What's the working rule is. Now, we'll consider the classical setup. What's that classical setup? A omega or AW is equal to B. Of course, A and B I obtained from the data. Okay, we consider the normal equations to solve and all that. Now, the best thing that I will do here is for linear regression, I'll be using principle of least squares. Principle of least squares to estimate the unknowns. Okay, for the linear curve that I'm going to approximate. Okay, from principle of least squares, what I will do is I will split or rewrite A as a x transpose x and B as a x transpose small one. Okay. Of course, regarding this procedure, if you want, I can talk a little later. But now, once I have this, what I will do is I will prepare the quantum states. We prepare the quantum states. Quantum state ket B. Okay, how do I write ket B? B by norm B. Okay, it is just a normal vector. I have normalized the vector. It's just a vector. I normalize the vector and form the quantum state. Okay, next what I will do, the next step would be quantum phase estimation. Okay, what is it that I'll do? On the matrix A, I'll be applying phase estimation given by U is equal to e power IAT. Okay, yeah. So once I do this phase estimation, what happens is each eigenvalue component Uij. Of course, spectral decomposition I will do. Okay, spectral decomposition once I will do, I will get something like this. I can write spectral decomposition of A as well. That would be something like Ui, Uj, I'm sorry. Of course, multiplied by lambda I or, okay, something like this. I mean, into the eigenvectors, if I do. Now, if I split it into A and rewrite it as eigenvectors, then it would be nothing but my spectral decomposition. Now, coming to quantum phase estimation, what happens is quantum phase estimation maps each eigen component to lambda j transpose in the ancilla register. As we have discussed in the previous videos, ancilla as for a temporary temp is like your temp. Ancilla register is a temporary storage for different things. Okay. What exactly happens is the eigenstate decomposition of B becomes beta j lambda j tilde it would be. Okay. Anyways, I will do a numerical problem to make you understand this. Now, once I'm done with this, I'll perform controlled rotation. Controlled rotation. What it does? Controlled rotation is a quantum way of transforming lambda to lambda inverse. Okay, or reciprocating the lambda value. So I perform controlled rotation on another ancilla qubit so that the amplitude of ancilla 1 becomes proportional to 1 by lambda j. Okay. So what happens? Lambda becomes 1 by lambda j. Lambda becomes 1 by lambda. Lambda becomes 1 by lambda. Of course, here I'm talking about not a normal just one value, guys. Again, there are they are very much complicated. Now, I made a mention of ancilla 1 bit, except the result of the ancilla 1 bit, I am least interested with the ancilla 0 bit, etc. So, for which I will neglect those terms. Okay. To neglect those terms, what I will do is I will uncompute the same quantum phase estimation. For what? It is also called to erase ancilla 0 values, which may form further entanglement. Okay. So for which what I will do, uncompute quantum phase estimation, and once I've uncomputed, unnecessary things will be erased from the ancilla register, or the leftover entanglement can be avoided. Finally, what I will do, I will measure the ancilla 1 bit. Measure the ancilla 1 bit. Okay. Hence, the system register contains a state proportional to the system register. Contains a bit proportional to A inverse B. Okay. A inverse get B. Okay. Let us check that with an example. Of course, when it is possible to do quantum linear regression, if you ask me, first and foremost thing is that A must be Hermitian. You will observe that in the example. Also, A should have well conditioned number, guys. K conditioned number, the highest eigenvalue by lowest eigenvalue. That number should be well conditioned. Of course, once the result is in quantum states, I transform it to classical states. Okay. I get the result usually in quantum states. I transform that to classical states. Okay. Let's take a numerical example and understand this. What I'm doing is, I'm considering A to be X transpose X. What is X I can give you here? You can cross check. Some matrix 1, 1, 1, 2. Y, small y, I'm choosing it to be 2, 3. Okay. So once I perform X transpose X, 2, 3, 3, 5. Obviously, A is equal to A transpose, or A is Hermitian, guys. In real sense, it is symmetric. In complex sense, it is Hermitian. Okay. Hence, next what I will do, B is nothing but, I have said that there is a proof for it using again principle of least squares only. Anyways, we'll look at that if needed. Now coming to this, what I will get B to be is 5 by 8. Okay. Yeah. Now, this is the classical way of doing it. Now, let us see the quantum way of doing it. For quantum way, what I'll be needing is, I'll be needing the eigenvalues. Okay. Compute eigenvalues of A. Okay. Det A minus lambda is equal to 0. This implies I'll get some lambda value 6.854. That is lambda 1. Lambda 2 is what? 0.14589. Now, if I take the condition number, guys, lambda, highest lambda value by lowest lambda value, it's reasonably good. Okay, because of which I can proceed according to the condition. Now, once I have this, I will as well find the eigenvectors, guys. How do I find? A minus lambda I into lambda 1 I into x1 is equal to 0, or xi I will say, depending on how many ever values are there. That many eigenvectors I will be getting. This is one eigenvector 573 0.85065. Of course, the ones which usually we do are all integer eigenvectors, but here I can get real eigenvectors as well. 850650 minus 0.525731. 0 point. These are the two eigenvectors that I have got using the above statement. Next, now we'll check whether they are orthonormal or not. Of course, next we have B na, normalizing B. That would be what? Ket B is equal to B by norm B. Okay, hence what I will get would be 1 by root 89, 5, 8. Right, so what would this value be equal to is 0.53033, 0.84852. This is the value of Ket B, guys. Okay, yeah. Once I'm done with this, I have the eigen basis. Okay. Next, see, B I can rewrite as eigen basis. I am telling now. Beta 1, U1, ket U1, beta 2, ket U2. Eigenstate. Eigenstate, yeah. Eigen basis. This is how basis. I will write eigen basis. Okay. What exactly is it? How do I find beta 1 and beta 2? Beta 1 is nothing but U1, inner product of U1 and B. Beta 2 is nothing but inner product of U2 and B. Okay. Yeah. So what happens once I find the inner product? This value turns out to be, this is 0.99999 something, almost 1. This value turns out to be 0.005. I don't think it's 3 zeros, it is 2 zeros. Once I have this, next what I will do is according to the procedure, according to the controlled rotation or whatever, I have to find lambda inverse, right? For which mod C by lambda J should be less than or equal to 1. With that condition, I will be choosing C. Choose C. Let C be equal to 1. Okay. For J is equal to 1. As I've written previously, what I will be getting would be beta J C by lambda J. Okay. So what I will be for J is equal to 1, it would be nothing but 1 by lambda 1. This is 0.14589. And then for J is equal to 2. J is equal to 2. 1 by lambda 2 would be 6.854. Okay. So you may think, what exactly, ma'am, you are trying to do if you ask me. Just see here. Suppose if I write ket W, it is nothing but something like A inverse B. Now my B is no more normal B. It is nothing but my ket B. Okay, of course, A inverse if I have to find. I've written the spectral decomposition for A. So what I will be getting would be lambda 1 inverse into beta 1 ket U1 plus lambda 2 inverse beta 2 into ket U2. If you find this value, this turns out to be something like 0.106, 0.106, guys. Okay. 1 by lambda 1 and 1 by lambda 2 I already found now. So this turns out to be that. Hence you can write. Okay. So what do you observe? Just see here, guys. If I take 0.106, it is nothing but my 1, 1. Okay. What if you ask me what is this 1, 1? This 1, 1 was my W. Okay, here if you see, yeah, this one. Okay, here when I am applying, I know A, I know B. Suppose if I start finding out what is W, it would be nothing but 1 is what I will get from this. Okay, and then in the classical way, and then if I do it here, if I do it here, if you can clearly see in quantum way also, this one, what is it? Get W, I've got it to be some scalar into 1 only. Okay. Yeah, if you have a doubt, I can just show guys what exactly I'm trying to talk about. Just see here how you got 1. If you think if I'm manipulating or something, just see. Suppose let W is equal to W naught, W1 and W2, guys. Now A is what? 2, 3, 3, 5, na? And this is W naught or W1 and W2. This is equal to what? I have 2, 3 as my, no, 5, 8 as my right hand side. Okay. Solve the system of equations now. 2W1 plus 3W2 is equal to 5. 3W1 plus 5W2 is equal to 8. Solve this and check. You will be getting W1 and W2 to be 1, guys. Okay, once you solve them, you get them to be that. Of course, this is the classical way of doing it. Quantum way of doing it is this is the way I'll be doing. What I will be doing, I'll be going with the spectral decomposition. Once I'm done with the spectral decomposition, I make a controlled rotation. After quantum phase estimation, I'll make a controlled rotation, and then I'll uncompute. This control rotation would give me this resultant, ket omega. This is how I'll be doing quantum linear regression, guys. Okay, thank you.